So we're going to continue our discussion of atoms, molecules, and ions by first taking a look at the most important tool that a chemist has at his or her disposal, and that is the periodic table of the elements. Now this is a copy of the periodic table that I like for a lot of reasons. For this reason, I've sent it to you via email, and I'm going to refer to this as your periodic table. It has a lot of useful information on it. At the same time, it's not over cluttered with information. There's only one tiny piece of information that I would change about this if I could, but I'll get to that a little later. As you see, the periodic table is a way of organizing the 118 elements that we know of. By exploring this particular periodic table, we can find very useful information. For example, in the upper right-hand corner of each box, you will either see a cloud, a cube, or a droplet. Now, as the key in the bottom left suggests, that speaks to the state of matter in which the element can be found at or near room temperature. So element number 1, hydrogen, we find in the gas phase at or near room temperature. As you go from left to right, you see helium, element number 2, similarly is a gas at or near room temperature. If you continue reading from left to right, you will see that element number 3, lithium, is a solid at room temperature. In continuing this, we get to element number 35, bromine, which we find on the right-hand side of the periodic table, being the first element listed that is found in the liquid phase at room temperature. There are only two elements that are found in the liquid phase at room temperature. That's bromine and mercury, element number 80. You'll notice that there are only a handful of elements that are found in the gas phase at or near room temperature. Most of them we find on the right-hand side of the periodic table. In addition, we can find out information with regards to whether the element is naturally occurring or whether the element is man-made. If you look in the bottom left-hand corner of each box, you will find either nothing or a tiny little stick figure. If you see nothing, then that element is naturally occurring. If you see a stick figure, that means that the element is artificially made or man-made. As it stands, if you look at element number 81, 82, 83, 84, leading up to elements 91 and 92. 92, uranium is the last element in order of increasing atomic number to be naturally occurring. Everything from 93 and above is artificially made. Also, if you look at element number 43, technetium, as well as element number 61, promethium, you will find that they are also artificially made. If you look in the bottom right-hand corner of each box, you will find either nothing or a tiny symbol denoting radioactivity. Starting at element number 83, bismuth, and going on to polonium and astatine, we find that these elements are radioactive. Now, radioactivity doesn't necessarily mean it's gonna get you. Okay, it doesn't mean that it's going to kill you. If you look at element number 83, bismuth. Bismuth is part of a compound that you might use, a pharmaceutical product, if ever you have upset stomach or any of those other ailments that the commercial speaks of. Pepto-Bismol, one of the primary the active ingredient in Pepto-Bismol is a compound called bismuth subsalicylate. Does that mean that Pepto-Bismol is going to get you? No. In fact, it does the exact opposite. It'll kind of help you out when you need it. Element number 95, americium, is found in many conventional smoke detectors. So there's a tiny amount of americium in several smoke detectors, perhaps even ones that are found in your office, your home, your work. Does that mean it's gonna get you? No. Radioactivity simply speaks to the stability of an atom and how over time these atoms can ultimately decay or break down to form other elements. I also want to speak about a particularly interesting feature of the periodic table that basically is a dividing line of sorts. On the left-hand side of the periodic table, we tend to find metals, as the label above elements 25 and 26 suggests. On the right-hand side, we tend to find nonmetals, as the label above elements 6, 7, 8, and 9 suggests. But where is the line? What line separates metals from nonmetals on the periodic table? Well, if you look at element number 13, aluminum, you'll see that all around aluminum there's a tiny blackened line. That line tends to step down on the right-hand side, going between aluminum and silicon, going between silicon and germanium, going between germanium and arsenic. That line, which looks very much like a staircase, is known as the staircase. It's also known as the zigzag line. So elements on the left side of the zigzag line are metals. Elements on the right side of the zigzag line are nonmetals. And we'll speak more about this particular line and this particular designation in a few moments. Now we're going to take a look at the organization of the periodic table. We tend to find that elements in the same vertical column tend to have similar properties. If you look at the vertical column that begins with element number 9, fluorine, followed by element number 17, chlorine, element 35, bromine, followed by element number 53, iodine. Yeah, I know you want to say iodine, but it's iodine. I'm not going to fault you if you say iodine, but it's iodine. Underneath that, we find astatine. Underneath that, we find tennessine. The simple fact that these things are named similarly should suggest that there's some similarity amongst these elements. If you move over one vertical column to where we see element number 2, helium. Underneath helium, we find neon, followed by argon, followed by krypton, followed by xenon, followed by radon, followed by oganesson. Once again, you might think that these elements have something in common with one another. Well, let's get away from the simple naming. Let's look at some properties. Look at element number 29. It's near the middle of the periodic table. Element number 29 is copper. Directly underneath copper, we find silver. Directly underneath silver, we find gold. These three metals are what we refer to as coinage metals because A, they are precious metals with significant value, and B, they are malleable, ductile enough, able to be shaped into coins. Now, I have no idea if element number 111, runtgenium, is malleable enough to be shaped into coins, nor am I going to speak to its particular value. But I can think of a couple of reasons why I wouldn't want to make coins out of runtgenium. It's radioactive. Now, in a moment, I'm going to get tired of saying elements in the same vertical column. I've got to find a way to shorten that. Well, I think I've done it. It turns out that vertical columns on the periodic table are known as groups. And if you go from left to right, you'll find that there are 18 groups on the periodic table. The first group starts with hydrogen. The second group starts with beryllium. The third group starts with scandium. As we travel all the way over to the 18th group, which starts with helium. Horizontal rows on the periodic table that go from left to right are known as periods. So the first period is made up of hydrogen and helium. The second period is made up of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, and so forth and so on. Now, the disjointed area at the bottom of the periodic table, the area where elements 57 through 70 and 89 through 102 appear, they do not represent a separate period, nor do they belong to a particular group. They are truly an island of their own. When we speak of the periodic table of the elements, we need to understand what the term periodic means. In the same way that a periodical is a publication that comes out in regular intervals, like a newspaper or a magazine. Your newspaper comes every day. Your magazines come every week or perhaps every month. The behavior of the elements suggests a certain degree of periodicity. There is a repeating behavior as we traverse the periodic table. If you look at elements 1 through 118, you will see that each of the periods can quickly be analyzed in the following manner. Elements in the first group on the periodic table tend to be very reactive metals. Now, hydrogen is an anomaly, so for the time being, we're going to throw hydrogen out of this discussion. All of the elements in group 18 tend to be very unreactive or non-reactive gases. So, if you think about that, each of the periods on the periodic table begins with a reactive metal and ends with an unreactive gas. So as we go from left to right, we go from reactive metal to unreactive gas, and then we start over with the next period going from reactive metal to unreactive gas. Some of the groups on the periodic table have special names. The first group, the group that includes things like lithium and sodium and potassium and rubidium and cesium and francium. These are called alkali metals. The next group, group 2, which includes things like beryllium and magnesium and calcium, these are called alkaline earth metals. The group 3 through 12 elements, that's a lot of elements. That's that kind of bulky area in the middle of the periodic table. Those 10 groups from groups 3 through groups 12 are collectively known as transition metals. So things like scandium and titanium and vanadium, all the way through nickel and copper and zinc. These things and all elements underneath those in the respective groups are called transition metals. Do you know what we call the elements in group 13? The group 13 elements. That's it. The same thing with the group 14 elements and the group 15 elements. But when we get to the group 16 elements, things like oxygen and sulfur, we call these chalcogens. Chalcogens. The word chalcogen is from the Greek meaning ore forming, O-R-E. These elements tend to be found in metallic compounds, metallic combination with non-metals that we call ores. Different minerals tend to include oxygen and sulfur and selenium. The group 17 elements are called halogens. Fluorine, chlorine, bromine, iodine, astatine are examples of halogens. The term halogen means salt forming. And lastly, the group 18 elements are called noble gases. Gases because they are all gases at or near room temperature, and noble for the simple fact that they tend to be very unreactive. They do not mix well with others, in the same way that nobility doesn't mix with the commoners or the riffraff. These noble gases tend not to play well with others. So helium, neon, argon, krypton, xenon, radon, and oganesson are all noble gases. Now, we spoke of the zigzag line before, that staircase that separates metals from non-metals. So if we were to characterize something as being metallic, some of the common properties that we tend to think of with respect to metals are a shiny luster, the ability to conduct heat and electricity. And metals tend to be solids at or near room temperature. Now, there's always an exception to the rule. I can think of a handful of exceptions with regards to shiny luster. I can think of a particular non-metal that has a shiny luster in its solid form, iodine. As far as conducting heat and electricity, graphite is a fairly good conductor of electricity, and diamond is a very good conductor of heat. And both of these are forms of pure carbon, which is a non-metal. And as is indicated, mercury is not a solid at room temperature. It cannot be hard for a mercury thermometer to work if mercury was a solid at room temperature. But these are just some of the characteristics that are typically associated with metals. Nonmetals are typically found on the right-hand side of the periodic table. Once again, we have to take into consideration hydrogen. Hydrogen, although it is element number 1, although it appears on the left-hand side, it is indeed a nonmetal. And if you look at your periodic table, you will see the lengths that have been gone to in order to exclude hydrogen from the metallic side of the periodic table. Take a look very closely at the zigzag line on your periodic table and see how hydrogen is actually excluded. Touching the zigzag line, we find a series of elements that we call metalloids, or sometimes semi-metals. Now, not all elements that touch the zigzag line are considered to be metalloids. So for this reason, we're not going to talk a great deal about the metalloids. Elements like boron and silicon and germanium. It turns out that these elements sometimes behave like metals and sometimes they behave like nonmetals. But unless told otherwise, we're going to treat elements on the left-hand side of the zigzag lines as if they are metallic, and elements on the right-hand side of the zigzag line as if they are non-metallic.